Hi everyone. Let me see if my microphone is okay. Got last time some complaint that the volume of my voice was too low. So I'm trying to see whether the volume can be better this time. So I know there's no interaction here, but if someone can hear me reasonably well, you can type OK into the chat so that I know indeed my voice will be okay. But you can write something like a louder. Okay, I saw some okay. Good. All right, let's get started. So we discussed word problem in last lecture. So today we are switching back to our discussion on arithmetical operations. And remember, a week ago we talked about addition over natural numbers. Of course, you guys have learned all of those things, right? You are generally assumed to be in grade 5 now. You have spent several years studying those arithmetical operations, addition, subtraction, multiplication, and division. And what we are doing is that taking a totally different approach to re-understand the number system and the associated arithmetical operations. And hopefully that way, for strong math students, you will get a fresh view of those concepts and learning something much deeper and much more rigorous than you would learn in school. And for other students who previously might have been struggling with math, hopefully now we are trying to help you catch up. Okay, that's the goal. So today we are talking about something really super important in mathematics. And those are the commutative and associative laws. And in a couple of lectures, we'll also talk about the distributive law over addition, multiplication over addition. So that law involves two operations, addition and multiplication. But for commutative and associative laws, they have both their application for addition alone and multiplication alone. And it's not surprising that why they work for both. Because as we will study just a couple of lectures down the road, multiplication is nothing but repeated addition as far as natural numbers are concerned. Remember, right now we are only talking about natural numbers, not even negative numbers. So, why those laws are so important? They are the fundamental laws for the whole mathematical kingdom. Because right now we are at the very beginning of a long journey of studying math. So we start with some simpler systems, and namely right now just the natural numbers. But as you just move along, we will soon add negative integers so that we will have all integers. Now we will study fractions. And by that, usually we only mean positive fractions. But it's straightforward to extend positive fractions to their negative counterpart. So with both positive and negative fractions, we will have rational numbers. And as you will see, probably you already knew this, integers can also be written as rational numbers. Well, natural numbers can be written as fractions. So that way we can actually unify integers with fractions together into rational numbers. And then we will add irrational numbers. Irrational numbers combined with rational numbers, we got all the real numbers. Okay, that's pretty much you will study before college Although in high school, you will also learn something called complex numbers with some imaginary part for each such complex numbers. But if you truly understand real number well, complex numbers are quite kind of straightforward extension, although they do impose some just challenges because they contain some so-called imaginary part. That's the picture, big picture down the road. But it's important to understand that for all those number systems, the commutative law, the associative law, and the distributive law, they all apply. That's a very important just a rule. And to deeply understand why that's the case, it's very challenging. So today we'll start with the simple case with only commutative and associative laws for natural numbers. Also, it's worth to mention that in some books and in many other places, you will hear the term commutative and associative properties. They mean the same thing. A modern and more accurate terms for those things are actually called laws. Although properties have been used for a long time, but we try to be as rigorous as possible. So in free Asian math, we'll use the term law rather than property for those things, but they are essentially the same thing. Okay, so let's talk about commutative law first. Remember, as I just mentioned, the commutative law has both a addition version and multiplication version. Today we'll only discuss the addition version. So what is the commutative law? Well, although I mentioned that this law applies to all numbers that you will reasonably learn before college, for now, we only limit this law to natural numbers, okay? So, for any two natural numbers, m and n, this law says that m plus n equals to m plus n. You probably knew this quite a couple of years ago already, and you never challenge it, right? Why this is true? It looks so obvious. If you go to some website or study in another curriculum like the great art of problem solving curriculum, their founder Richard made some very good video which is available on YouTube. By the way, I will give you that assignment today, talking about the associative and the commutative law. He used some funny just analogy when he wear multiple hats, different than one hand just holding several hats and the other hand holding several hats. He argued that if he just add them up, it doesn't matter which hand holds what hats. That's a great analogy, okay? But mathematically, why this is true? Let's just say we have two numbers, okay? 3 plus 5. What this law really says is that 3 plus 5 equals to 5 plus 3, right? Very simple and very obvious. But why? You cannot merely argue it's true just because it's obvious. You can use some good analogies, essentially like what Richard did in his video. Say, if you add those squares or boxes together, you have 5 first, then 3 second, 5 red plus 3 green. You reshuffle them, change their relative position, it doesn't really matter how you add them, right? If you put the 3 green before the 5 red, you should get exactly the same total. This is so true and so intuitive, but it has two problems in this argument. First of all, use the example 5 and 3. How about 5,000 and 3,000? You really want to do something like this, enumerate 5,000 and 3,000, put all rows, just 5,000 boxes on the paper, and then swap them, try to show this is true. Even we can intuitively see why this will be generally true, but still, this is not what we call a mathematical proof. Okay, this is very intuitive, but this is not a proof. A second problem with this, of course, is this argument itself, it's inherently based on some additional assumptions. That is, you argue that when you swap this water, nothing will change, right? Yeah, that's so obvious. Except if you ask why. Why it's true that if you swap the two positions, this fundamental thing will not change. We just count the total number, right? That's exactly a big problem if you really want to get to the bottom of mathematical statements, because we want to have a rigorously built system where if we go back to the origin of our argument, we think there's no logical flaw or logical hole or anything similar to a crack on your foundation of the house. If there's a crack on the foundation, the whole building may collapse one day. Not today, maybe after the storm, the house may collapse. So it's really important, either for your curiosity or for the sake of just making yourself feel confident about our system, it's worthwhile to ask questions like this. Why 3 plus 5 equals to 5 plus 3? Again, if you base your reasoning on some seemingly obvious but almost impossible to explain things, like say, if we swap the red boxes and the green boxes here, nothing should change. That's not a rigorous mathematical proof. So, what do we do? Well, remember when we define our natural numbers, we assumed 4 axioms, right? Namely, we have 0. We assume that's a natural number, and it serves as the starting point of our counting process. Then we further assume there's a so-called increment operation on all the natural numbers. Of course, at that point, we merely had 0 only. We did not have anything, but we assume there's such a fundamental increment operation. Now we impose, or meaning that we give you 2 more assumptions, which were used to prevent when we do counting, we will never have just a circle so that we count back. So 1, 2, 3, 4, 5. Then we go back to 0 or even go back to 1. So we did those 2 additional axioms to prevent such just a misbehavior. But with those 4, we were able to define what natural numbers are. We know when we count from 0, 1, 2, 3, 4, we can only go forward, can never wrap around because of the 4 axioms we imposed. But we actually deliberately did not mention a fifth, a very important axiom, which would be needed to enable us to prove something like the commutative law. And that is something called mathematical induction. If we did have that, the fifth axiom called mathematical induction, which by the way would not be appropriate to introduce to fifth graders like you guys. So we are in the position that we cannot actually prove the commutative law, meaning that this law would not be a theorem. A theorem meaning that you can prove. So because of that, we have to assume commutative law. Even for the simplest natural number case, we just assume it's true. In other words, we treat it as an axiom. So that actually makes our life much easier. So when you have this question, why you have this thing, it's true because we assume it to be an axiom. But still, we want to give you a quite reasonable interpretation of its truth. So we mentioned that we want to use the number line, which you are seeing here, to study numbers. For now, we only have positive integers, natural numbers. And we mentioned how we actually mark those integers on the number line, right? It's all based on our counting or how we actually define the natural numbers. As it turned out, this is a great tool for us to understand things like a commutative property as well. So we will give that a try. Okay, so look at this. We have 3 plus 5. Then on the number line, we have 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so remember how we mark those numbers. We mark those numbers based on our counting process, right? We first choose a point 0, any point. Then we choose another point, still kind of arbitrary, but we specify it's on the right-hand side of 0, so we call it 1. But once we have fixed those points, we cannot choose other 2, 3, 4, 5 kind of at will. Why? Because of that increment operation, we assume it's true, the same increment operation for every natural numbers. So now we see that 2, the distance between 1 and 2 must be exactly the same as between 1 and 0 and 1, which by the way, we call that unitless. And from that point on, we can continue this process. We get another uniqueness. We mark that point as 3, another point 4, and so on. And this is actually essentially the same thing as how we define the natural numbers, right? Remember how we define the natural numbers? We start with 0. That's our first axiom. Because of our second axiom, we assume there's an increment operation so that we can have 1 increment on 0. That's what it is. And then from 1, we can take the same, get a 2, and 2 get a 3. And how we define addition? Addition of natural numbers is effectively just repeated counting. So if you recall, 2 lectures ago, we defined m plus n. What is m plus m in our definition? Remember in math, we build things from the ground up. Forget about what you learned in your school math for this addition operation m plus n. it has to be based on how we actually define it. How did we define it? We define it, we start as the number m, then we count forward, plus 1, plus 1, plus 1, plus 1, and we do this, repeat this plus 1 operation n times. And what is m plus 1? M plus 1 is nothing but this very first increment definition generalized to any number m. So m plus 1 is simply increment 1. M, sorry. Increment m. So that's our definition of m plus 1. And then m plus m. So that's how we get this idea. What is addition? Addition is nothing but repeated counting forward. Now we want to intuitively understand why m plus m equals to m plus m. So let's take a look at the first one, m plus m. That means that we have to choose our initial point, which is m. And we know m, for example, in the context of 5 plus 3, or let's choose 3 plus 5. That means that we will choose point 3, right? And then plus 5, meaning plus n, then we count it forward n times, in this case 5 times. 1, 2, 3, 4, 5. Okay. So, really, we are arriving at point 5. But remember, 2 lectures ago, we also discussed we use the length of a line segment on the number line to understand the value of a number. So essentially what we are doing is to combining the length of those 2 line segments. Okay, I'm using different color now. Okay, so we have a line segment 3, which is from 0 to 3. Another one is from 3 to 8, right? Remember how we denote this. And the length of these line segments is actually our second number being added to the first one, that is 5. We know that. But remember, we proved the theorem. We proved the theorem that if we assume this line segment can be slided on the number line, when we perform that sliding, it can fit into another slot which has exactly of the same length. In other words, we can slide this line segment, which is from point 3 to 8. If we move it into 0, 5, this slot, this should be exactly the same line segment. So that means that if we do a sliding, now for this from 0 to 8, we slide it into 0 to 5. This should be exactly the original line segment. Look, this is an intuitive geometric interpretation. It's still not rigorous, but can give you a better or more confident feel about this. So we can slide the line segment from 3 to 8 into 0 to 5. Okay, so we do this. But similarly, we can also slide the original 0 to 3, this line segment, into 5 to 8. How do we know that? Because we actually can count from 5 to 8. That's exactly the same as from 0 to 3. Remember, we know from 3 to 8, that's 5, or from 5 to 8, that's 3. So if we can do this, then we can easily see that essentially the first addition, 3 plus 5, it's really just a combination of two line segments, which is from 0, 3. Then you combine that from 3 to 8, those two. Those two line segments share a common point, which is 3. So in other words, those two line segments are concatenated back to back. It's a seamless combination. There's no hole between the two, and there's no overlapping, because the ending point of the first one, which is 3, is exactly the starting point of the second one, which is also 3. So 3 plus 5 is really the combination of those two line segments. On the other hand, now you can easily see 5 plus 3, when you swap the order, it's really, by the same argument, you can see that it's a seamless combination or concatenation of 0 to 5 and 5 to 8. But what we just did is just merely move two line segments on the number line. And there was a big assumption when we started that. We said that their length should not change for either one, right? Because their length should not change, now we combine them together, their total length should remain the same. It's still the same two line segments, and their length should not change when we slide them. No matter where we slide them, their length should not change. Therefore, we argue that their total length must remain the same. Okay, what is any potential problem? Can you just argue, say, this argument is solid, therefore we prove this commutative property just based on this straightforward geometric interpretation? Not really, because you still need to argue why, when you swap two line segments, their total length should not change. That's fundamentally the same thing as commutative property itself, or commutative law itself. If you just make that argument to prove, trying to prove the commutative law, you have not achieved anything. Essentially, you just repeat the same very problem just as your argument, and that's not acceptable. But in this case, it does give you more confident agreement to say this is generally true. 3 plus 5 equals to 5 plus 3, because the geometric interpretation is just when you swap them, it's really sliding those two on the number line, and because the two will not change their length, the total length must be the same. Okay, so this is nothing but an intuitive explanation. It's not a rigorous proof. If we do have mathematical induction available, this can be actually rigorously proven. But that's beyond what we need to know. So from this point on, we just assume this commutative law is generally true, and that's what we call as an axiom. Okay? So, very important, this is generally true beyond the natural numbers. It's also true if the two numbers are any integers, including negative integers, even any rational numbers you haven't officially studied yet, or even real numbers, or even complex numbers. This law is always true. But to understand why it's true for those more complicated numbers will be significantly more challenging than what we are trying to understand now. With positive integer natural numbers, such a geometric interpretation is so obvious. It becomes much more challenging, say, if we have two irrational numbers, which we haven't studied yet, but you can imagine what that will look like. Let's just say pi plus square root of 2. Of course, again, I understand some of you may not completely know what we are talking about, but pi is irrational numbers, and square root 2 is another irrational number. When you add those two, why this equals to square root 2 plus pi? And what are they in the first place? What is the meaning of pi plus square root of 2? Well, that's just another real number. What we are claiming here is that the sum with the resulting real number in this case must be exactly the same resulting real number. In this case, the 2 points, remember each real number is just a point on the number line. The 2 points must be exactly the same. They result the same point on the real number. Of course, that will be for another day, which will be quite into the future. So for now, you just take face value, understand this is important, and it's true. So now we have to discuss order of operations before we talk about the associative law. And what is order of operations? And then we will talk about the parentheses. I'm pretty sure many of you have already learned this, but we take this opportunity to get a much more rigorous discussion and want to remove some of the bad things your school math has done upon you. All right, we'll see what that is. So what is order of operations? Before we can even discuss that, we must talk about the concept of mixed operations. So all those arithmetic, addition, subtraction, multiplication, and division. Later on, we will learn exponentiation. All those are just so-called operations, right? So in all those cases, actually, they involve two numbers, even for the future, like exponentiation. For example, 2, oops, not here. 2 to the power 3. What does that mean? That means 2 times 2 times 2. So even in this case, you see that there's a number 2, which we call the base. By the way, you don't have to worry about this for now. This is just some quick discussion. This exponent or the power is another number. Generally, we call this exponent. Okay, so even in that case, you have two numbers to work with. Of course, addition, subtraction, multiplication, and division, they all involve two numbers. And you get a third number, which is the result. But in general, when we have mixed operations, meaning that you have something called an expression, which involves more than just one operation. Because once you have the first operation, you want to use that, the output from that first operation as the input into another operation. Why we want to combine them together? There are two reasons. First, that's much more visually direct. And secondly, it shows the logical relationship. For example, if we have two additions, 3 plus 5 equals to 8. Now we want to use the outcome of this operation as the input into another addition, say 5 plus 7 equals to 15. When you write those two, not only more time consuming, and you lost a way to show the logic between the two, or the connection between the two. People seeing this will not immediately recognize that this A means the second A. this logic connection is lost when you separate them. Yeah, you may still guess maybe this A is the same A here, but there's no indication that it's generally true. This A could mean a totally unrelated quantity that happens to be A, right? So in this case, what we will do, we will combine those operations together. We write 3 plus 5, and we will treat this, the result, as the second operation. We want to use the output into the feed that into the second operation. And this one is the second addition, which requires two numbers. And we know the first number comes from the first addition. So how do we do that? Generally, we write it into this way, plus 7. Okay? So there's a problem here. Is that how does this actually tells you that the first one, the result, is actually the second one? Well, this may look natural, right? We usually do things from the left to the right. So if that's the case, what is addition defined? Addition is defined with two numbers. There's no way you can read the whole thing as just one operation. That's not well defined. So you have to start with something that is meaningful, and that is 3 plus 5. So naturally, we think 3 plus 5 is the thing that you need to do first. And then, if you get it, you naturally read from the left to the right. You think about that's the result 8. Then you take the next operation, which is the plus here, addition. Then you think about this should be naturally evaluated as 5 plus 7. So this is just how natural things should look like. But this is really important to understand. When we have those things, we mix multiple, meaning more than one operation together. That's what we call a mixed operation. But this is a very simple case. Say we only have additions, right? And what if we have multiple different operations, subtraction, multiplication, and even later explanation? When all those things are mixed together, how should we know the particular order that we should perform such operations? Well, you can say, why don't we just follow the same so that it's always from the left to right? Well, it is possible to do that, but there are multiple issues with that. First, we want some flexibility. Sometimes the logical order among those complicated operations could be kind of just inconvenient for us if we have to put them into from the left to right order, and sometimes it's simply impossible. So we really need to specify a well-accepted, well-defined set of rules about how we perform such complicated operations if we mix them up. So with this mixed operation, we need to have a set of rules. This is a collection of rules mandating the order in which we can perform those mathematical operations. But the goal is to evaluate a given mathematical expression. In other words, for something like 3 plus 5 plus 7, we want to know ultimately what, this is something we call a mathematical expression, what is the final value or result that we expect to get. Okay, so that's where we need this set of rules collectively called the order of operations or operator precedence. So it's all about how we set up a set of rules and then everybody agrees with them. All right. So that when we talk to each other using mathematical language, we can easily understand what the other side means by that. Just like if you talk with someone who only speak, say, French, and you only speak English, you can never understand each other. So the default order, which we actually just saw, is very important. When you have something called of equal precedency, like in this case, we have two additions back to back, then the default order is always from the left to the right. Okay, so if you have addition only, it's always from the left to the right. That's the default order. But sometimes we have more than that, and we do want to expressly change the order somehow. So we set up a general rule like this. Well, as you will see later, and this is truly important, you don't have to understand this completely for now, but we want to give you the full rules. First of all, you have different precedences of operations. In general, addition and subtraction are the easiest. And there's a very good explanation why is that. So the next level would be multiplication and division. And the further next level would be exponentiation. And finally, we have this symbol called parentheses, which is a catch-all overriding rule, can make addition and subtraction having a higher precedency over, say, explanation or multiplication and division. So parentheses is of the highest precedency, which can override any other order. But without the parentheses, all those operations, they have a predefined order of precedency. And remember, this is nothing but an agreement. We can say addition and subtraction have higher precedency over multiplication and division. And then our whole world will be different in terms of how do you evaluate mathematical expression. But this is nothing but agreement. Also, there's a very good justification for that, and you will learn that. We already mentioned that addition is nothing but repeated counting, right? But you will learn soon multiplication is nothing but repeated addition. And explanation is nothing but repeated multiplication. Because of this fact, which you will learn, it's not difficult to understand why we want multiplication to have a higher precedency over addition. And we want exponentiation have higher precedency over multiplication. On the other hand, you will also learn subtraction is nothing but another way of doing addition. As the result, addition and subtraction, they are of equal importance. We don't say addition is more important than subtraction or vice versa. Similarly, division is just another way of stating multiplication. Therefore, once again, we treat multiplication and division at the same precedency. I heard, this is actually real, I heard some of you have teachers told you that addition has a higher precedence over subtraction. That's ridiculous. The teacher is not just wrong, the teacher should be fired. That's just plainly ridiculous. Okay? So the rule is like this. parentheses, whenever you have it, it will change the order. It has the highest precedence over anything else. In fact, we use parentheses to override the other order of precedence. And without parentheses, then we will have explanation before multiplication or division, which will be before addition and subtraction. Okay, with that understanding, I want to do one more thing. This rule has been summarized to you, at least by some teachers, called this acronym PMDAS or PAMDAS. This is a mnemonic. You should not try to memorize a rule like this by relying on such a mnemonic. You should memorize this rule by understanding why we want it. That is, multiplication is repeated addition. Exponentiation is repeated multiplication. Therefore, we will want multiplication to have a higher precedence over addition, and explanation having a higher precedence over multiplication. At the same time, subtraction is just another way of saying addition. So addition and subtraction, there's no discrimination between the two. They are of equal importance when they are both present. If we don't have any parentheses, the order is just the default order. That goes back to the rule before this. The default order is from the left to the right for operations of equal precedence. Same thing between multiplication and division. So with that understanding, now we turn to some simple facts. So let's just say we have this one. 15 plus 8 plus 23. What is the order of operations? We have two additions here. Therefore, we don't have any parentheses. We goes to the default rule, which is that from the left to the right. So we do 15 plus 8 first, which gives us 23. 23 add another 23, we get 46. So now, this is not very interesting, but if we add a parenthesis to the first one, oops, there's a typo here. There's no, I'm sorry, this should be never here somehow. This one get it here, so I will delete that. Okay, so when we have this first parenthesis, it did not change anything. It's exactly what we would do without a parenthesis. However, this just gives you an emphasis that we want to do the first addition first, right? 15 plus 8 first. So this parenthesis achieves nothing but give us a just strengthened understanding of the order of operations here. But what if we group the second and third, put them into a parenthesis? Now the order of operation got changed. In this case, we must evaluate 8 plus 23 first. And using the output of this addition as the input into the first addition as the second number being added. So we plus 15, 15 plus, in this case, it will be 31. So in this case, mathematically, it's a totally different expression from the second one or the first one, which are the same. Although, as you will see, the result will be the same. And that's what we will talk about in the associative law. But now, we know we haven't reviewed subtraction yet, but we do want to give you a heads up. Well, the order here is critical. When we have 23 minus 15 minus 8, we have two subtractions here. So the order goes to the default rule, which is from the left to the right. So we do the first one, 23 minus 15. That gives us 8. And then we use the output of this first one, which is 8, as the input into the second one. 8 minus 8, that's 0. Okay, so just as in the addition case, if we group the first one, put the 15 minus 23 minus 15 into parentheses, we achieve nothing because that's already the default rule anyway. But this does give us a visual reminder we want to do this first, okay? Which sometimes can be very helpful. Okay, what if we do the second one first? That changes everything. What is 15 minus 8? That's 7. So now with this 7 into the first subtraction, 23 minus 7, that's 16. It's very different from the first one and the second one, which gave us 0 as the final evaluation of the expression. So you can clearly see that this parenthesis in this case completely not just change the form of the expression, also change the value. And this is very different from the two addition cases above. Why? Why this is the case? Well, it's because associative law does not work for subtraction. We will talk about that, but that's not today's purpose. This is just as a kind of just preview of why the associative law is so important for addition. Okay, so here we come the associative law for addition. With the understanding of how the parentheses work, we will be able to say the associative law for addition in the exact way. And the law is exactly like this. You have 3 natural numbers, L, M, and N. The first one, L plus M plus N. You can, as you can tell, the first parenthesis is not necessary because this order is already the default order. In other words, L plus M plus N without the parenthesis is exactly as what we saw on the left-hand side of the equality here. The associative law says that when you have L, M, N put in this order, if you put the second and third, group them into a parenthesis first, and evaluate that expression, you will get exactly the same result. Okay, so L plus M first, M plus N equals to, if you add M and N, the second and third first, then use that result into the first addition, add that to L, the final result should be exactly the same. And that's exactly what associative law tells you. And it's very important to understand, in this case, it does not even allow us to say this could be something like associative law means that L plus M plus N equals to, well, the parenthesis here is optional, but we put it there. This equals to L plus M plus M. In this case, we are grouping the first and the third first. Of course, this still works. But this is not the associative law. This is a result of the associative law, but this is not the definition of the associative law. Associative law merely says that when you have 3 items, 1, 2, 3 together, adding the first 2 would be the same if you add the second and third first. So the grouping here is strictly if you group those 2 first. It does not even give you a choice, say, I want to group the first and the third first, then add the second. Yeah, we can actually show this is also the case. Why? Because we have commutative law, right? Because in this case, you can actually perform a commutative law first, convert this into L plus m plus n. This will be based on the commutative law, because when you add rows 2, you can swap the order. Then you can redo the grouping thing. But that's not what the associative law says. So the associative law is strictly when you add 3 things up, it tells you if you put the first and second together, it will be the same as if you put the second and third together and first. Okay? So how do we know this is also true? Once again, exactly as in the case of the commutative law, we cannot rigorously prove this without the mathematical induction assumption. But once again, we can use the number line to explain why this works, right? So we first have to understand what is L plus M. That only comes from our definition of addition. What is L plus M? You start at this point L on the number line, then you count forward M times. Essentially, that gives you L plus M. We already know that. So L plus M is nothing but you combine 2 line segments. The first one is of the length L from 0 to L, and the second one is from L to L plus M. That's what addition means, right? Because you group them together, the result is another number, and we know that is at this point L plus M, right? That's our very definition how addition works. So what to do if you add another n? That's just further counting. From this point, L plus M, we further count forward n times. So this time, you get to L plus M plus n, which is nothing but you count from the point of L plus M n times forward. So the left-hand side of the expression or the equality is quite easily understood. This just involves 2 steps of counting. First, we start at L, count forward m times, get a result, then continue to count forward n times. And the final result is just L plus M plus N. That came from our very definition how addition works. Okay? So what is L plus M plus N? This is quite difficult, okay? Because we use parentheses to change the order of our operation in this case, you have to evaluate M plus M first. So by our definition on the number line, if you want to get M plus M first, you have to start with 0, get to point of M. That's our first line segment, which is 0, M. This is line segment. Then you count forward to N. So this is M to M plus N. This is the very meaning of M plus N. You get those 2 line segments geometrically combine them. But in order to prove, or intuitively not really prove, to understand why this works, so on this number line, we have to look something like this. M starting at the very beginning, then another line segment of length N comes in second, then the other final piece L comes into the last place, the third place. But all we have done is just moving those 3 line segments around, sliding them into different positions, right? So this line segment sliding argument is almost exactly as what we just did for the commutative law. We already agreed whenever we slide a line segment on the number line, its length will not change. And because of that, once we have done this, the right-hand side it's still a symmetry combination because what we are trying to do with the second part, we are trying to actually use the commutative law we just agreed. We want to show this is true. And that came from the fact that we moved this one, the M, then N, then L into that order. So once we show M plus N plus L is the same as this guy, then from here to here is merely the commutative law we just agree upon. So the logic is like this. We first show that this one is the same as this one in red. Now we use the commutative law to show this one. By using the commutative law, we can get this order. Okay? So that's a geometric interpretation of how the associative law works. Now, here comes a super important thing. Based on both commutative and associative law, we have this very important result. Now this is a theorem because we have already agreed that both the commutative law and the associative law work. When we combine them, we reach this theorem. That is that for any collection of natural numbers, adding them in any order gives you the same sum. What do we mean by this theorem? First, for any collection of natural numbers, that means that you are not limited to just two numbers. You can have 3, 4, 5, 1 million natural numbers. You want to add all of them up, but in any order you choose, as long as each number is being added once and exactly once. That's how we do what we mean by adding them up, right? You cannot add the same number twice, or you skip some of them. You cannot do that. Let's just say you add all of them up. Any order you choose. How do you choose the order? With the help of the parentheses. For example, you list 100 numbers, 1, 2, 3, 4, line them in a row. Let's just say you add the 5th and the 26th first. Well, you can choose that order. So you can change any order with the help parentheses. Eventually, if you add 100 numbers, how many additions you will perform? You will perform exactly 99 addition, right? Because you one by one add them up. This theorem says that out of those 99 operations, any order will give you exactly the same sum. Okay, and this can be proven with the commutative and associative law. Also, the technical details of such a proof could be very kind of messy because the notation could be complicated. But we will just give you an intuitive explanation why this is generally true. Let's just say we have 10 numbers, okay? Let's say 1, 2, 3, 4, 5 plus 9 plus 10. Those 10 numbers. This is, we write them down, and this looks like a natural order we want to use. Now you want to say, I want to add them in any particular order at my pleasure. I want to say put the 3 first, then plus 8, plus 7, plus 2, plus 9, plus 1, whatever. You continue until you finish all of them. I think that's a 4. And then finally, you have, maybe I will put 10 here. Okay, I want to do this in this order. How do you show the first one, the result of first one is the same as the last one? Well, you think about it. With both commutative and associative law, you can do a series of gymnastics, mathematical gymnastics. The idea is that we only sketch an intuitive idea. You can somehow say through a series operation to put a 3 into the first position. How do we do that? Well, you have to use something called mathematical induction, right? You can say, I want to group everything. I assume that's something I will be able to do. Then I will be able to swap this thing with 3 and so on until this whole thing goes to the first. Or you can say I group whole thing 1 plus 2 first, then swap the position between this group. So that way you will put 3 into the first position. Now we have only done one step. We put 3 into the correct order and say this is correct because now we can put 3 into the first place. But that's still different from the last one. But you can continue this process by this kind of swapping, put everything into the correct until you reach at this particular order. Okay, so as long as you have both the commutative law and the associative law, you start with a particular order, you can arrive at any other order. And this is so useful. Okay, so we will give you two very simple examples. There's a famous story about Carl Gauss when he did this famous addition, right? 1 plus 2 plus 3 plus 4 all the way plus to 100. So Gauss, at a very young age, some legends say at age 10 or another said at age 7. I don't know which one is more accurate, but he was at that time. Remember, that was several hundred years ago. Certainly, math was not as advanced today. So, as a young child, he independently discovered this trick, which is truly remarkable. He say that you can add 1 to 100 first, 2 to 99 first, and continue with those two 100 numbers. You form 50, exactly 50 pairs, and each pair gives you 101. Because after that, you have 50 identical 101. You add them, you can do multiplication. Therefore, the result is 101 times 50, because now you have 50 pairs. The result is 5,050. So what exactly did Gauss here? Nothing but follow the theorem we just said, right? With such 100 number, you can do the addition in any order you wanted. I can certainly put 1 plus 2 first, 1 plus 100 first, then plus 2 plus 99 first, plus 3 plus 98 first, until I have 50 plus 51 first. So that way, you can clearly see this is nothing but 101 times 50. Okay? So all Gauss did is to use the commutative and associative law, reshuffle the order of the summation. Okay? It's very important. So let's take one more look at this theorem, which says that very succinctly, but you have to understand its mathematical meaning. For any collection of natural numbers, adding them in any order results in the same sum. It doesn't matter. This is a very powerful theorem, actually, if you think about it. And we can use it for a lot of good things. For example, let's do some mental math. You can do some very fast calculation. Of course, the numbers have been made up for you. If we want to do this expression, we want to add three numbers first. 398 plus 168 plus 102. Well, what we will do, without any careful thinking, you want to add the first two numbers up, right? You get 398 plus 168. That's not very obvious. very quickly. You have to do something, then you add 102. But a careful student or smart student would observe that you can change the order of the addition. You add the first and the third first. Why? Because it's very obvious that they kind of complement each other. You have 98 and then you have 2, they add up to 100. So 398 plus 102 gives you 500. And now you add 500 to 168. That's super easy because you have 2 zeros after 5. That will give you 668. So this is very obvious, right? So adding one more, make it a little bit more complicated, but actually even easier. Now we plug in another number, but not adding that at the end. We plug in that into the second and the third in the first example. Now we have 4 numbers. So what do we do? Well, once again, you can recognize that you want to combine 376 with the third number, which is 224. That will give you 600. All right. And similarly, you combine the second and the fourth, 168 plus 432. Once again, you have another 600. So at the end, you add 2 600 together. That's 1,200. Okay, so I know 99% of you already knew this trick, but it's important to understand why we are unable to do this. And this comes from the super important commutative and associative laws for addition over natural numbers. Of course, from this point now, we will expand such rules. Eventually, we will extend to negative integers as well. But for now, we already have a powerful weapon at our disposal, and that is the theorem we just talked about. If you do addition, any order will be fine. And later, we will extend this to other numbers, not just natural numbers. The same theorem will hold up. Okay? I will see you on Friday. Bye.